Let's run through some RC circuit examples real quick. A 480 ohm resistor is connected to a 1.5 microfarad capacitor, which doesn't have a charge on it, in series with a 6.11 volt battery. So what's the initial current? Well, before capacitors are charged, they basically act like a wire the moment they're connected. This basically means that I have a 6.11 volt battery connected to just a 480 ohm resistor. So I can use V equals IR, plug in my values, and get 0.0127 amps. Now, the problem asks for it in milliamps, so I need to do a quick unit conversion. There are 1,000 milliamps in 1 amp, so this becomes 12.7 milliamps. Part B, what is the RC time constant in seconds? Well, RC time constants are just R times C. Now, one thing I need to be very careful of is that all my units are base units. I'm already clear with the resistor, that's in ohms, but with the capacitor, that's microfarads. So I'm going to have to convert that to farads. And that's 1.5 times 10 to the negative 6 farads. Ohms times farads will get me units of seconds, and in this case it happens to come to 7.2 times 10 to the negative 4 seconds. Now, I'm going to jump to part D before I do part C, because I like being myself. What is the voltage on the capacitor after one time constant? This tells me that the time that has passed is the same as my time constant. And my time constant is just RC. So the time that has passed is 7.2 times 10 to the negative 4 seconds. So I'm just going to plug this into my charging equation since my capacitor is charging. And instead of t, I'm going to put a tau there. Doesn't matter what tau is, since my time that has passed is the same as a time constant, this just simplifies down to my EMF, which is 6.11, times the quantity 1 minus e to the negative 1, and that lands me with 3.86 volts. Now this is actually going to help me solve part C, because anytime you have electrical components in series with each other, be it two resistors, two capacitors, or a capacitor and a resistor, the sum of the voltage from the first plus the second equals the grand total voltage. So that means my resistor voltage is going to be my EMF minus my capacitor's voltage. And that comes to 2.25 volts. Now I just need to plug this into V equals IR. So 2.25 volts dropping over a 480 ohm resistor will get me a current of 0.00469 amps, which once again, they ask me to convert that to milliamps, multiply by 1,000, that's 4.69 milliamps. So that's how to handle it when a capacitor is charging. How about when it is discharging, when it's releasing that energy? Let's say we've got an 8 microfarad capacitor that's initially charged to 50 volts. It's connected in series to a 500 kilo ohm resistor. So how long will it take for the capacitor to release this voltage and end up down with 4.1 volts? Well, for this, I'm going to use my discharging capacitor equation. It's a little bit different than the charging capacitor equation. To start, I'm going to have to figure out what this time constant is. A time constant is just R times C, making sure I convert back to base units. That's going to be 500,000 ohms times 8 times 10 to the negative 6 farads. That gives me a time constant of simply 4 seconds. Well, now I can just plug my values into this equation. I know I've got 4.1 volts left at the end. I started with 50, e to the negative t over tau. Now I'm going to divide 4.1 over 50 equals e to the negative t over tau. Then I'm going to take a natural log to get rid of this exponent. Since I know my tau value is 4, now I just solve for t and end up with a final solution of about 10 seconds. That is for a discharging capacitor.